Wir werden uns dann still und leise verabschieden.
Ja, mach das. Okay.
Good morning, everybody.
Good morning.
Morning.
Yeah, a small introduction round, or I mean, everybody knows me. But I don't know if you already had contact before. So
Yes, hold on.
Yeah,
a
I think
moment.
I think it makes sense.
Yeah.
okay, so as you invited, Peter, so I think the best is you introduce yourself with your position, and then all the other colleagues step by step introduce themselves. Maybe give a 1 minute introduction what they have already done in the ERFA project. So that we have a 10 minutes introduction round, and then we will leave you into all the details and secrets of bill of materials and detailed drawings, which is Peter's knowledge.
Yes, of course. Okay, I will start. Peter Knobel, my name, and I'm responsible here for the design of chutes, ducts, insulation, and also in this area we have that conveying pipes that are running mostly through complete plans and quite long and all that stuff. So I'm here at Polysius for now 18 years, and I'm the team leader here, and I would like to show you later all the secrets and details, as Mitya says, regarding conveying pipes, which are later in the coming months applicable for this ERFA conveying project.
Yeah, thank you very much, Peter. So the next for the introduction, Kwong, everybody knows you, so I will not ask you. Maybe Kai will be the next one.
Okay, our turn. Hello everybody. My name is Keung. I have worked for ThyssenKrupp for 9 years. Almost of time I work with the process duct. Currently, I in charge of responsible for this team. Plan engineer team here, and at the moment, of course, there are not of new thing for me. So I need to I have joined a lot of training from back home for such as plan design, E3 by Zoran, and now by Conveying by you, Peter. And I think it's very lucky when we receive the necessary program training from back home. Yeah.
Thank you, Kwong.
Thank you. Yeah. I think I will introduce. My name is Nguyễn Kim Thu. You can call me Thu for short name. My background is pie shred analysis for oil and gas and LNG plant. So I want to expand the career. So I try to join the plant design. So I just joined the Thyssen Polysius around over 3 months. So I start to learn about E3D and everything. So I very excited to model and control something like that. The building, the conveying pipe is more bigger than my old field.
Okay.
My old field only adjust the piping in the oil and gas to ensure that all the nozzle is under allowable, all the support is okay. But working with the plan design it's very big, so I can do so many things. For example, move the building. The first thing I do in my career. Yeah. So thank you. I hear that Peter, you working in Thyssen 80 years. 18 years.
Yeah.
18,
Wow.
yes.
Yeah.
It's
Look,
the
you so young.
Drawing.
Yeah. Thank you. That is all from my side.
Thank you too. So,
Yeah.
who will be the next? I think Kai, it's your turn.
Yes. you still remember me, Mr. Media.
Sure.
Hello, everyone. My name is Kai. You can call me Kai. I used to work in a petrochemical about 2 years. Have experience for a factory. But when I take part in TCN group, it's very excited. And today I'm very excited when Mr. Peter in can guide all of them about shoot and duck. Is I think when become plant design engineer need to learn many things because it's very large to learn. So thank you, Mr. Peter, have spending your time to guide all of them. Thank you.
You're welcome.
Thank you, Kai. So, next one, Son, please. You.
Yeah. Let me introduce about myself. Good morning, everyone. My name is Phạm Quang Sơn. You can call me Sơn. I have around 5 experience as a piping straight engineer in the oil and gas plant. So now I would like to explain my experience in the plant. So this is the reason I joined the position as the plant engineer at TCN Group. Yeah. Thank you. Nice to meet you, Peter.
Thank you. Then I think Duke, it's your turn.
Yeah. Okay. Nice to meet you, Peter and Chia. My name is Vũ Văn Đức. Call me Đức. Okay. My background is civil structure and engineering, and I have about five experience in detailing, and after that I work in a design team, and now I come to plant design, and it is a new thing with me, and I think I get more knowledge in plant design. Thank you.
Very good. So, and the last one, Tue, please, your turn.
Hello, everyone. My name is Tuệ. I have over 1 year in TCN. Before I work as a detailer position, and then I have been joined in plant design for 2 weeks. I start with learning E3D software. In the new position, I hope I will and receive the support from the own. Thank you, everyone.
Thank you, Tue. So, yeah, perfect fit. 10 minutes introduction round. Good team. And then I think we will not wait for a long time. I will hand over to Peter. I will leave you alone for all the secrets and details. Good luck, good learning. Thank you very much, everybody. Peter, it's your turn.
Thank you, Mitya.
Yeah.
Okay. Then let us start. So as I said before, I would like to go into the details of conveying pipes. That means I will not talk so much about the plant design itself, because the routing of those ducts is it's depending on the plant design, how we can attach those ducts to buildings and whatever, and so that's more a plant design thing, and I would not like to go in detail. Of course, there are some special things coming from the design of those conveying pipes and that are relevant for the plant design that I will show you, but not about the routing and all that stuff itself. As Kwong sent the invitation to this meeting or to this training, you all of you got this our planning documentation for the conveying pipes, right? Is that correct?
Yes, we have.
Okay, perfect. I will take this planning documentation, more or less as a schedule or as a how we can go through this training.
Yeah.
So I will share this. So I think all of you have hopefully read this this documentation quite well and are a little bit aware of this. So of course, in the first thing I would like to start with the pipe itself. So with the diameters, with the wall thickness and all that stuff. As you can see here in this documentation that we have quite a huge variety of diameters. Let's say the first 3 or 4 are upcoming in the last 1 or 2 years for our Catch for Climate plan. So they are not that often, so we have them once in all that time, but the following diameters, let's say 80 up to, I don't know, 250, 300, they are quite common in the last years and decades. And these large diameters are also quite rare. So I cannot imagine, as I said, I'm here for 18 years, and in these 18 years we have one conveying pipes with 400 and all the other things we don't have. But nevertheless, we have them in our standard, and we are basically able to do those ducts or those conveying pipes, sorry. So here you can see that we have these standard diameters. We are completely using also standard pipes that you you bought from the market, so that are not like you have it for the process gas ducts, those banded pipes made from plates. So they are completely bought in and what you get from the market. For all the conveying pipes, we usually only have one wall thickness. This is always this 6.3 millimeters. It doesn't matter what diameter we have always this 6.3 millimeters. Also, the material is always the same. It's common mild steel, so nothing special, no 16MO3 or stainless steel or whatever. We don't have this. Especially for later for the flanges, we come back to that later. Usually it's that are standard flanges coming from European norms with a pressure rate of PN10. That's also what you usually get when you would like to apply standard flanges. What you usually get quite easily from the market. So in the last years we learned that flanges, let's say PN6 or PN2.5, it's quite difficult to get them from the market, and maybe they look lighter, but in the end of the day they are more expensive than a standard PN10 flange because it's you can get it easily from the market, and what you get easily is quite cheap. So that's also quite easy here. What materials, wall thicknesses, and so on are used, it's always the same. So it's not really rocket science. Okay. Yes. Two.
I have a question because yesterday, a few days ago, about the diameter, when I explained to my colleague, but they asked to me, what does this mean of inside width of basal band and pi? Because when they read this, they understand that outside pi diameter, for example, DN40, they understand that outside diameter is 48.3 mm and inside a pipe is 40 mm. So they understand that the thickness of them is around 4.150 mm. You understand? They deduct the outside to inside and.
Okay, yeah, I can explain you. So this is, as you said, is the standard outside pipe diameter, and sometimes we have conveying pipes. I will come to this later. We have special bands or elbows. You can say what you want, bands or elbows. And in these elbows, sometimes we have a lining that is done from basalt. So it's a volcano material that is given inside this band, and at these bands the inside diameter is, let's say, 40 or 50. So it's these values, and it is not for the straight pipes. So the straight pipes are as you already said, it's 48. Pardon?
I think that we have
my connection.
Yeah.
Then you can continue.
So from a straight pipe, the inside diameter depends on the outside diameter and on the wall thickness. So this one has nothing to do with the inside diameter of the straight pipes. It is only for this basalt bands. I will send you later quite a lot of examples and catalogs where you can see this, but I will share this. So here you can see from our supplier about this basalt bands. So it's a supplier from Germany, and you have here those bands, and as you can see here in the each, here you are coming with the straight pipe. It's a standard pipe, let's say DN80 with this, I don't know what has it. Let's have a look. It's outside 88.9. And then this basalt band comes, and that has an inside diameter of 75. And this basalt band, this is this part here. So that's our items that we that are bought in, and that are completely ready. And as you can see, the outside diameter increases, and the inside diameter is more or less the same as we have it here on the straight pipe. And what is written in the table is that this inside diameter of this basalt band is 75. Is that clear too?
Yes, it's clear for me. Thank you for your explain.
Okay.
Peter, for the the rate of flank PN10 the pressure for inside release, the pressure for by conveying in lower than 10 bar, right?
Yeah. I think they are. Yeah, it depends a little bit on the pipe itself, how long is it, and all that stuff, and what pump is before, and so on. But as far as I know, the pressures are around 2 or 3 bar overpressure. That's what I know, but I'm not in detail. So we are quite far away from those pressure.
Yeah, it's about 4 to 5 times.
Yeah.
Okay.
Because I know that's the nominal pressure only for calculate the resultant pressure equivalent in flank when it's the moment acting on the flank connection.
Yeah. That's right. Okay. So let's continue. Coming from the standard pipes to the bands or elbows. I call it bands here, but you can also say elbows. So as I said before, there are different types for those bands. That depends a little bit on what material is conveyed in the conveying duct. So sometimes it's abrasive, or sometimes it's not wearing, and then you have to choose the correct bands. But in the end of the day, we here from back home give you the instruction what band has to be used for that conveying pipes. So that's nothing you have to choose. That's coming from us. It's already calculated in our projects towards the client, and that's what is coming from our side. So as I said before, we have this basalt bands. That's what I showed you before, and then we also have this option to have a normal standard steel band, and on the back side we have a kind of concrete elbow. I can show you that quickly. So here you can see those concrete bands, and what is meant is that it is a normal band, and then we have on the back side where the wear of this conveyed material can occur, we have concrete on this back side. So when the duct itself is worn out, then you still have this concrete on the backside, and you get no hole in the duct. So those possibilities you have, or if the material is a non-wearing material, let's say raw meal or some kind of that stuff, then you also have bands without any wear protection. The radius is depending on the duct diameter, on the pipe diameter. In general, we have this 2 meter radius, but nevertheless, when you have small diameters, then the radius can also be smaller. And for really large diameter from 300 upwards, we have also a radius of 2.5 meter. Then coming to these basalt bands, as I said before, those bands are completely bought in. That means we have this supplier. In this case, we have it is called Kallenborn. It's a German company, and they from there we bought this basalt bands. And as you can see here, these basalt bands are flanged in and have specific angles that can be chosen, and also the radius can be chosen. So as you can see here, we have those angles which are possible, and the radius is coming from above. And so you how can I say it? You stick one band after the other and flange it together, and at the outgoing side of this band you always also have a straight part of this basalt pipe behind. The reason is that the material is laying here when it comes from here, then it is laying here on the outside, and to get the flow in this conveying pipe a little bit normal, it takes a straight pipe to get a little bit normal, and so that the wear is not also affecting the straight pipe here behind the band. So that's the reason why we have also a straight portion of this basalt band behind an elbow. Which straight pipe has to be applied after which elbow is written in this table here. As you can see here, that you have the nominal diameters, and you can see, let's say for DN200, you have a straight basalt band of 2 meters behind the band. So that's what is written here. Okay, then we have
Peter.
Yes,
I have a question. Just if the space is not enough space, the house, what is the minimum for the stress by length? Because you know when we routing the pipe in the band, so there's some place that have the net space that enough and not enough to place 2 elbow near close.
So the general rule is that you have this 10 times of the nominal diameter should be the straight pipe. So that's the general rule, and that is also reflected here in this table. But when you have, let's say, two 90 degrees bands that are coming next to each other because it's required from the plant design, then you can also do that more or less directly behind each other or with a shorter straight pipe in between, because then then you already go into the next direction, and you also continue then with a basalt pipe. So you have that first band, and let's say you have only a short portion of 500 millimeters as a straight, and then you continue with the next basalt band. But then you are always still in basalt, and that's then no problem. But nevertheless, the thing is, it should be avoided to do quite a lot of these double elbows. So usually you should have a distance between the elbows, because the flow in the conveying pipes has to recover itself and has to accelerate after a bend, and for that you need a straight portion of this conveying pipe. And of course, let's say in one conveying pipe, it's not a huge problem to have one or two of this double elbows. So let's say two 90-degree elbows behind each other. That's not a big deal. But if you have 3, 4, or 5 of them, then the process depth has to know this, and they have to consider this, and they have to think about if the pump is strong enough to bring the material completely through the conveying pipes. So that's the reason. Usually, so that is somewhere written. It is also somewhere written in this document that you should have a specific distance between two elbows, so that the material in the pipe can accelerate again.
Okay. When the flow, I think when the process engineer calculates a sizing for the blower, you literally consider the number of bands, because, for example, if I found that my routing have the classing with some structure, I have to increase the number of elbow to 1, 2, 3. Maybe the number of elbow will increase, the pressure drop will increase, so they have to sizing the size of blower one time again. So
yeah, that's the point. The thing is that usually the design of this is done in a first step in our project phase. So let's say before we are awarded the contract, and the sizing of the blower is firstly depending on this. In the end of the day, of course, there has to be maybe a recalculation and to consider all that stuff. But sometimes when you have these double bands, that maybe can be a problem. So that has to be considered quite carefully by process depth.
The position of the center, the position of this.
Okay. As said before, you can also have these common steel bands, so they are quite easy. It has no specific wear protection on it. The radius is as set above, depending on the diameter of the conveying pipe. What's important for this, that's more or less later a fabrication thing, is that I can show you here in these drawings. When you later are preparing the detailed drawings of such a conveying pipe, then it's good to have this band and not doing here, let's say, a side weld. It's better to do the side welds minimum 500 millimeters before and after the band. The reason is that those bands, you cannot purchase them from the market. So they are bended in workshop, and if you have these straight portions in front and after the band, then it's easier to clamp the pipe into the machine and do the rolling of this band. That's the reason why it's better to have this 500 millimeters before and after the bend. So that's a fabrication thing. Later I will also send you quite a lot of examples from workshop drawings that have been done in the past. This is quite new, this information from workshops, so maybe you will not find this in all these workshop drawings I will send you, but yeah, for future it should be good to consider this.
Yes.
The same applies here to the concrete bands. There you also have this straight portions behind and in front of the band, but the reason is the same. It's better for fabrication to clamp the pipe in the machine.
Yeah, the first time I think the length between that belongs the band. Maybe the first time I think that is to avoid the deformation of band, because when we bending the pipe, maybe the face of the band maybe not the circle anymore, maybe it's the ellipse. The first time I think, so now I know the reason why they put the pipe 100 mm before and after the bend.
And
Thank you.
Yeah. Let me check it.
Okay. Yeah, that's so. Normal steel bands are quite easy. You can use angels as you would like. That's something other than here for the basalt bands. There we have this nominal angels, so you're a little bit restricted in what you can do for the routing. But if you have a pipe or conveying pipe or only with steel bands, or later here with this concrete band, you can do angels as you would like to. Nevertheless, usually those conveying pipes are horizontal or vertical, but basically you can do an angel as you would like. So for the concrete bands, I will show you a drawing, because here in this view it's not so detailed. Just give me a second. Yeah, here you can see. So here you can see a typical of those concrete bands. So it's not true to scale. It's only a typical, but here you can see quite good the principle of those concrete bands. So you have the pipe with the band and also with the straight portion behind. And here on the back side you have this concrete. And what you can see here in the section view is that you have a plate which is a welded construction and which is on the back side of the pipe. So it's welded tight on all the sides, and it's only open from one side. So here you have a bottom plate, then you have here a hollow space, and on this side it's open. And later on side you can lay down this band on the ground with this portion showing upwards, and then you can fill the hollow space here completely with concrete. So that's the principle of those concrete elbows. And in the past, the colleagues from Pune always described this concrete elbows in this table. So as you can see here, we have these typicals with all these letters, and you can find the letters here, and they describe the dimension of those elbows via this table. So not all of the different elbows for one conveying pipes are detailed on the drawing. It's only via this table. So it's I think a quite easy solution, and not doing so much drafting on the drawing itself. Okay. Any questions to this concrete elbows?
I think it's clear. Could you send this drawing to us?
Yeah. I will share you. I will share later quite a lot of documents, and that you can have a look also in detail again on it. I will share this with you, of course. Yes.
How for the maintain if maintain if the e-bow is break?
And then you have to cut it off completely.
Cut and replace by new one.
Yes.
Okay.
Yes.
Yeah.
So that's coming from our process department. So they decide which wear protection shall be used for conveying pipe. So when we have conveying pipes with very abrasive material, don't know, like coal or whatever, so that are quite aggressive materials, and then we usually have this basalt bands. And as you saw before, those basalt bands are completely flanged, and then it's quite easy to replace a worn out band. These concrete elbows are used for, let's say, medium abrasive materials, and where we don't expect so much wear, and then these ones are a quite good solution because they are definitely cheaper than these basalt bands.
Yeah, it's cheap because it's mild steel, right?
Yeah, it's mild steel, and you only have to fill it with concrete, so that's also quite cheap, and yeah. That's the reason. But the decision on which band the conveying pipe is going is coming from process depth.
Yeah. Okay.
Okay. Yeah. So here you also have, as I said before, this requirements regarding the fabrication, so 500 millimeter before the band, and after the band you have also this straight portion, and that is more or less the same length as you have it here for the basalt bands. So let's say if you have a conveying pipe that is a DN200, the straight portion after the band should be 2 meter. Now here in this passage of the planning documentation, you have the reference to that table. Okay. Then for the flanges, as I said before, usually we have this European standard. So I think that should be known to you. It's usually then PN10. So that's whenever we connect to to the blower or to the pump, or when we connect later, we have we'll also show you we have expansion pieces inside the conveying pipe. That expansion pieces also have this PN10 flanges, or when you have branches or valves or whatever, usually all of them have this PN10 flanges. One exception from this are the basalt bands. So I will show you again this thing from the catalog, from the basalt bands. And as you can see here in the picture, you are coming, let's say, with a DN100 straight pipe. And usually for this DN100 straight pipe, there also is a reflecting flange for DN100. But as you can see here, the basalt pipe outside diameter is larger than this, let's say, DN100. So here you cannot use this standard flanges. And the company of those basalt bands they have their own company standard for the flanges. So they are reflected here, and I will always give you this catalog part so that you can see the dimension of those basalt pipes, and that's the only exception. What I will do in future, I have to talk to Martin Cohn and some more people here. As far as we know, in the meantime, this company also is offering flanges not according to their company standard. They're also offering basalt pipes with flanges according to this European standard, and maybe this gives us the opportunity not only to buy in the basalt pipes only from this company, and then maybe we can also go to other companies and to get a little bit cheaper, but yeah, that's future stuff currently. Okay, yeah, that's also written here. For the basalt pipes, we have this company standard from the supplier. As you maybe know it from the process gas ducts, then we usually have the flanges, and the duct itself is insert into the flange, and except the last 5 millimeters, and then it is welded from the outside and tack welded from the inside with a fillet weld. Here for the conveying pipes, it's a little bit different. Here you always have it like that, yeah, here you can see that we stick in the pipe completely into the flange and only have a fillet weld from the outside. The reason is that we would like to avoid a kind of gap or something like this here. So in the process gas ducts, the duct is coming from here and then it ends here, and there you will get a kind of gap. And that's what we would like to avoid for conveying pipes, because maybe this could be an initial point for wear. And also when you have conveying pipes for coal, then maybe some coal is settling down in this gap, and that should be or must be avoided, because every settlement of coal is a potential risk for explosions or all that stuff. Okay. So that's a little bit different to what we are doing for the process gas ducts.
Yeah. So it is well welded one side is different with the process gas duct.
Correct.
Is it strong enough, right?
Yeah. That's not the problem. Yeah. So that's never had problems in the past.
Okay. The past is important.
Yeah, of course. Yes, so that's the difference for the flanges compared to process gas ducts. Then what you already see here is the type of gaskets we use. So at the process gas ducts, we usually have this cord, what we are using, and for conveying pipes, it's usually a flat gasket. Maybe you know it from Catch for Climate, where we also have this flat gaskets at the process gas ducts, but there we have this, let's say, this special shape of this flat gasket. So it looks like a cord of pearls, and here we have a flat gasket that has not this shape as we have done it for Catch for Climate. I think you may remember, right?
Yes, I remember. It is very special.
Yeah. So here it's a little bit simpler. You have a flat gasket, and as you can see it right here, you have that flat gasket which is inside the bolt circle, so it is only here, and it's only a flat gasket with a even inside diameter and outside diameter. So no special shape. It's only a ring, let's say.
Okay.
So quite simple. Important is that the inside diameter of the gasket is equal to the inside diameter of the pipe. It has the same reason as I said before. We would like to avoid a gap here, and the gasket has a nominal thickness of 3 millimeters. And when you are tightening the screws, it's not possible to completely flat down the gasket. So in the end of the day, it's, I don't know, 1 millimeter or 1.5 millimeters thick. And if you don't have it until the inside diameter, then there would be a gap, and that's also the same reason we would like to avoid the settlement of coal, and we would like to avoid initial points for wear. So that's important that we have the same inside diameter as the pipe.
Yeah. Okay.
The material for those gaskets is also always the same. It's according to a Polysius standard. It is called Nova Press Universal. When we are starting with the first conveying pipes, I will show you the material numbers and all that stuff that you need to know for the parts list. Okay, then coming to the supports, and maybe that's later on also a thing that Tu is interested also for the loads. We have a general rule that the supports should be around every 6 meters, and for this standard distance, despite if the conveying pipe is going horizontal or vertical, we have calculated standard loads. They are also here in this documentation. In the end of this documentation, maybe you saw it already, and these standard loads are they are calculated with a good add-on and calculated roughly, but it gives us the opportunity to give loads directly to the structural designers quite early. So usually for conveying pipes we are only using these loads, so we are not doing special calculation for each conveying pipe. We are using the standard loads, and that's it. So in the end of the day, there are not real calculations, as you maybe know it from chemical and petrochemical and oil standards.
In petro and chemical, maybe the support span beyond the size and content inside the pipe. For example, the size TN 14, I think the 6 meter is very, very long. Maybe the deformation in the middle space.
Yeah, but then in the end of the day, the duct is, or the pipe is completely filled. So that's maybe the difference. So we have here a conveying pipe, and it's a mixture of air and dust, and so the pipe is never completely filled, because then it's stuck and you will never get it running again. So that's a little bit different to what is in chemical or in petrol, where you have liquids that are going through the pipes, and So okay. So we usually have this standard distance, and what is also a difference to maybe to petrol or chemical industry is that we are using a loose and fixed point system, and if you would like to use this fixed point systems, you will also have to consider about a possible expansion and expansion joints in the duct, and we try to we try that the conveying pipe is not like in petrol with this Lyra elbows and deformation of the duct itself. We try to compensate this thermal expansion and all that stuff over expansion pieces. So, and that's then in the end of the day the reason why we can standardize the loads, and why we don't have to calculate every single conveying pipe. Okay. As I said before, 6 meter fixed point, more or less every 60 meter. Can be less, but if you have quite long and straight conveying pipes, I don't know, 200 meter or something like this, then you have to add expansion pieces in between. So that's meant here with this 60 meters. Supports in general.
Peter,
yes, please.
For for the expansion tube, is it same with sliding part in Osaka stock, right?
It's more or less the same, yes.
Yes.
Yeah.
So I concerned about the length of expansion tube. How many try of expansion tube? I saw in the VE document they only one expansion tube EU in the by conveying.
Can you repeat it? I don't get the point.
In the gas stack, the length of expansion joint it depend on the heat expansion, but for the by conveying, I can't find the the length.
Yeah. So the point is for the conveying pipes we have not this huge difference regarding the temperatures. So the conveying pipes are running around 50, I would say maximum to 100 degrees. And this distance between two fixed point for this 60 meters is depending on this, let's say 100 degrees. And what displacement an expansion joint can bear is depending on this temperature and also on what this expansion joint can move. And there is this 60 meter coming from. So it's standardized. So it's not like for process gas ducts where you sometimes have only, let's say, 80 degrees and on other process gas ducts you have 400 degrees. That's not what we have here for the conveying pipes.
Okay.
So the temperature range is quite narrow.
Small, yeah.
Small, yes. Okay.
Okay.
Then we have some different types of supports. They are also standardized. We have supports for horizontal conveying pipes and vertical conveying pipes. I would show this in these pictures. So here you can see the different types for the supports. We have loose points, which is with this U-bolt around, so it's more or less only a strap which is around. Then the fixed points are only beneath the conveying pipe with a side welding. So then it is the fixed point. Then for basalt pipes, we have this Son, can you mute your microphone? Thank you. Now it's on. Okay, thanks. For the basalt pipes, we have this type of fixed point, and this type of fixed point is flanged in between two basalt pipes. So this whole pattern, what you can see here, is the same which is coming from the basalt pipes. So it is flanged in between, and with that you can design such a support. And then for vertical, quite simple. We have this pipe brackets. If it is a fixed point, then the pipe bracket is welded to the conveying pipe itself. If it is a loose point only, then the side weld has to be leafed.
Peter,
yes.
For the selecting the size of support, do you have the table or reference to try to select exactly the size of support, because there are not of diameter for the pipe conveying.
So for all these supports we have standard drawings, and the selection which drawing and which parts list number or material number has to be chosen depends only on the diameter. So let's say for a 200 millimeter pipe you have only one of this type of support. So that's quite easy. I can also show you an example. So here you can see type of support again. So it's a loose point for an horizontal duct, and you can see here all the different pipe diameters what we have, and here you can see the parts list numbers what you have to insert into the parts list.
Yes.
Can you send to me the standard drawing? Because
of
in
course.
the first project I build the tool to build the loose point support for the E3D, but I beyond the other standards, so maybe the length of the C channel is different from you.
Yeah, that's right. But usually the standards I will send you later, of course. Yes. But all those standards are also reflected in the E3D catalog. So you should find this type of support with this specific height here for the specific diameter in the E3D catalog.
Because I cannot find E3D, so I have to build the new one when I try to join the training conveying pipe before.
Okay. Yeah, maybe that for that you have to talk to Uli Sternberg. How to find those standard supports in E3D in the catalog. So I'm not a specialist in E3D, but I know that they are there. Yeah, so as you can see here, for all these different types of support, we have these standard drawings. Not all of them are in a table. Sometimes we also have, let's say here for the fixed points. I don't know. So for every diameter we have one drawing, but nevertheless the principle is more or less the same. So for all these different types, we have standard drawings which are in the catalog. Okay. Yes, Kai?
Yes, Mr. Peter. I have a question about U-Bone. I work FA project, so I see U-Bone only used for horizontal pipe, right?
Yes, more or less. It's only allowed for horizontal pipes. When you have quite short sections that are vertical, then you can also apply this U-bolt to a vertical pipe.
Yeah, because I see the existing silo. They also use U-bolt for vertical pipe. Yeah.
So here you can see it. That's exactly what you mean. So we are talking here about vertical conveying pipes, and let's assume you are running up a silo. Then maybe you have at the bottom of this vertical portion you have a fixed point. Then it should be this one as a fixed point.
I also use vertical fixed point.
And but then when the silo is not that high, so here I would I quote that 4 supports in a row. You can also use this one for the vertical pipe. And let's assume this 6 meter distance. Then you get a height of, I don't know, 24 or 30 meters. Okay. So then now coming to this expansion tubes or expansion joints. Also for this we have a standard. As I said before, for the flanges, they have this standard flanges, and these expansion tubes, they have a specific length which displacement they can bear, and you can see it here. And on this specific displacement, let's say this 60 meter difference is reflected from, and also from a temperature of around 100 degrees. So we have that standard for this. I will also show you one example. So here you can see this expansion tube. It's more or less a kind of a sliding piece. So two duct pieces which are stuck in each other and tightened by a cord, which is pre-stressed. And here you can see that the flanges are you can turn the flanges. So there's a collar, and these flanges can be turned. So then it's a little bit more flexible during the erection. And these flanges are, as I said before, standard flanges from the European standard. And as you can see here, this expansion piece can bear quite a lot of, or can bear quite a huge displacement. So it's around 80 millimeters, which you can stick it into each other. So that's quite good, and it also allows us that we don't have that much stresses on the conveying pipe itself, because it's more or less load free here. Of course. Yes.
Peter, can you back the drawing for the expansion tube? I see the bone M20, the item 13. Is it?
Yes.
What is the purpose for this bone?
It's on one. It's more or less a guidance for the conveying for the expansion piece. So as you can see here, you have this flange and this flange. So you have three pieces of this long bolts, and you can see it.
Yeah, I can see in section AA.
Yeah. So and that's more or less a guidance, so that it is not twisted to each other.
Okay.
And the other bolts here, those ones, they are for pre-stressing the gasket here.
Yes.
So here this black area is the gasket, and then there is a small round bar which is going completely around, and it is here you can see it better. So this is this round bar. It's welded here in this outside duct, and these are the gaskets. So it's a cord, and with those bolts and this short pipe section, it can be pre-stressed and to get the gasket working.
Yeah, understood.
Peter,
Yes.
when I see the drawing of expansion tube, I think this expansion tube only allow for compress, not allow for extend.
Yeah, it depends a little bit on how it is built in. So here you can see the different dimension, and we also always have this drawing. So here you can see all those expansion tubes or expansion joints that we have for the different diameters, and here you can see the installed dimension, how it has to be installed. And this is a length which is in between, so it allows a little bit of decompression or longing of the duct, and also allows quite a lot of decompression of the duct, so or compressing of the duct. So these are these 80 millimeters. So when you are preparing the drawing, then the expansion piece should be built in with this length, and then it allows this displacements here. Yes. So as you can see here, for all the different diameters, we have standard drawings that can be directly used, and can also be used directly in the parts list. Yes.
I see. Maybe they set the dimension of the dimension of expansion tube is 580, so it can be compressed 80 mm and can extend 49 mm.
Correct.
I see. Thank you.
Okay. Yeah, so we have standard drawings for that, so that's quite simple to use. What is important here around the expansion tubes is that we have that an electrical bridging has to be built in, completely overspanning the expansion tube. You can see it here. Here's an example for this expansion tube, and we always have this electrical bridging here around. So that's more or less also something that you know from the process gas ducts. Then the other thing, sorry, I have to drink something because I'm talking too much.
Yes.
Just give me a second. Okay, that's better. Yeah, what's important for this expansion tubes is that usually, as you can see also here in this detail drawing, there is more or less a conveying direction that is given. So in this case, when you have a horizontal duct, then the conveying direction should be here from the left side to the right side, because it's optimal for the gas flow or for the flow inside the conveying pipe. But as I said before, conveying pipes, there's quite a lot of dusty material in it, and what we also have to avoid is that when the expansion tube is compressed, so let's say it is compressed completely, then this point is here, and then we have this annular gap, and let's assume we have not a horizontal pipe, we have a vertical pipe, then it is very important that this gap here, or here also at the bottom, is always looking downwards. And that is what is shown here. So here we have this horizontal pipe, and then the conveying direction should be following the optimal flow of this expansion piece. So here we have this inclined portion, or this cone piece, and it should be in from the left side to the right side. I think that is clear. And but when we have a vertical conveying pipe with this expansion tube, then it is important, you can see it better, that this annular gap, what you have here and here, is always showing downwards, so that no dust can accumulate here in this gap and maybe is later on blocking this expansion tube. So when you imagine this expansion tube is turned around by 180 degrees, then this annular gap is looking upward, and then dust can settle down in this gap. So that has to be avoided completely. It's not optimal for the gas flow, but yeah, we have to do this compromise because yeah, the dust settlement, or to avoid a dust settlement, that's more important, especially for coal. There it's really important that you have no dust settlement in the dust in the pipe. Okay. Then what we also have from the standards are special silo inlets. All of these silo inlets that we usually use, you can also find them in the E3D catalog. I will show you some drawings that you understand better. So here you can see such a silo inlet or silo inlet. So you're coming here with this with your conveying pipe, Then we have a completely bored-in rubber expansion joint. So this is a bored-in part, depending a little bit what displacements you have here, and also what material is conveyed, because then you have to have a look regarding the rubber. So that's a little bit special, and this is a completely bored-in part, so you don't have to bring it to your parts list or whatever. And then we have this standardized silo inlet, and it's for we have some different parts of it. For smaller diameters, we have this one, and later on for really huge conveying pipes, let's say 400 or whatever, then we have bigger ones. And this silo inlets usually have this tangential airflow, and the airflow is going here and then going a little bit like in a cyclone downwards into the silo. Yeah. So that are standard parts that can be directly used, and usually should also in the E3D catalog. So yeah, there are some different types. Here you can see it looks more or less the same, but it's the tangential airflow is on the other side, and also it is quite high. So it's nearly 2.5 meter high, and that's sometimes is important for the plant design when you are going up vertically to a silo, and then you are going horizontal on the roof of the silo. Then you maybe need this height. That's the reason why this inlet is a little bit higher. And then, as said before, we also have the possibility for larger conveying pipes. I think this is up to 400. I mean. Yeah, here it is also written 400 is the maximum conveying pipe, and the silo inlet. So this one is 800. Yes. Then we have this electrical bridgings, as I said before. They shall be at all expansion tubes or expansion joints, and also at all flange connections, because we have this flat gasket in between, and there is no, let's say, electrical connection between the flange halves. So that's the reason why we have to use this electrical bridgings. Can also see it here in this typicals for the flanges, where we always have this electrical bridging. But for that we also have standard drawings, as you may know it from the process gas ducts. Behind every expansion piece we have a measuring socket that has to be applied there. So it's also a standard part. It's DN25 or R1.5 inch, and don't know. Yeah, here you can see it. So that's behind every expansion tube. We have this manual measuring socket. So this gives the guys later on site the possibility to do some pressure measurings during commissioning, and that's why we have this measuring sockets. Then sometimes there are pipe branchings in the conveying pipe. The pipe branchings are usually completely bored in. So yes, please.
Peter, for the measuring sockets, who will design the measuring socket? Is it in by conveying scope or other?
No, it's in the pipe conveying scope. So so it's a standard drawing. You only have to apply it behind every expansion piece, and it's a standard drawing, and I can also show it to you. So here you can see that measuring socket in detail. It's a socket with a plug in it, with a screwed plug in it. So it's a standard drawing, and it only have to apply it at or after each expansion tube.
Okay. It's apply after expansion tube only.
Yes.
Okay. Yeah.
So whenever you have an expansion tube, you should apply it. So quite easy.
Yeah.
Okay. Coming back to this pipe branchings. As I said, they are completely bored in. What's important for pipe branching? So important is that the gas flow before the pipe branching should be straight. So it's not good to have an elbow directly before the pipe branching, because then the gas flow is maybe one-sided in the conveying pipe and then hits the pipe branching. Maybe there's a flap inside the pipe branching or a shut off flat gate inside the pipe branching, and then the gas flow is hitting only in one spot and is wearing out this pipe branch. So it's quite important it's good to have a straight portion of conveying pipe before the pipe branching. But that's more a thing for the previous plant design. Yes. Then one special thing. I think it's not for now for this ERFA conveying contract, because there we don't have it. But for other contracts where we have large process back filter, there is always a so-called pre-coating conveying pipe. So the large back filters have to be, so the backs in this back filter have to be pre-coated with dust, so that they are working good. And for this purpose, there is always a small pre-coating pipe which is going in the process gas ducts before filter. So the fan is running during commissioning, and you have that gas flow in the process gas ducts, and then some dust will be pushed into this process gas ducts and also in the filter, and is pre-coating the filter bags. And for this we have this conveying pipe. It's always a DN100 conveying pipe, and at the end I try to show it to you. Okay. I have to go to the other screen because it's only an AutoCAD. So here you can see this conveying pipes. It's coming down from the ground floor, and a silo truck can be connected to that pipe. So here's a blind cover, and then it's going up. And here you can see it better. And then you have that process gas ducts, which is going to a process filter, and then this pipe is going down onto this duct. And here we have a special nozzle which is connected here to the duct and spraying some dust into the process gas duct and also then later into the filter. So this duct is quite standardized with the nozzle here. Maybe somewhere it is shown larger. No. Here you can see it better. So this is this nozzle So the conveying pipe is coming here from the right side, and then you have this welded construction as a nozzle, and here it's a kind of fan-shaped guide plates which is in the nozzle and which is spraying the dust into the process gas duct and widening up the dust flow, let's say. But yeah, that's nothing for Erfacon. It's maybe later for other contracts where we have process gas filters. So that is described here. As I said, always DN100, and then we have this standard nozzle which can be connected directly to this DN100 conveying pipe. These conveying pipes or the nozzle should always looking downwards onto the process gas duct to avoid dust accumulation here. So it's not advised to have this nozzle going upwards into a process gas duct, because then it would be completely stuffed with dust, and then it's not working in the end of the day. Okay, then some things regarding the duct pieces itself. So the duct piece itself can be up to 12 meters long. That's when you have a straight portion and long conveying pipes. So 12 meters is something that you can stick into a container, and also it avoids later on site too much side welding of the duct sections to each other. It's also the thing that we try to avoid flange connections. So we only have flange connections when we have these basalt pipes, when we have these expansion pieces, or when we connect to something that is attached to the duct. So let's say the blower or the pump, or when we have a branching, of course, then we have flange connections. But for the conveying pipe itself, so when you have a long straight section, we don't have flanges every 12 meters. We will do side weldings here because every flange connection is a potential risk of a leakage, and that's why we try to avoid those flange connections. Then regarding fitting lengths, it is written here. The fitting lengths should be in every straight portion of a conveying pipe. That's more or less the same what you know from the process gas ducts, where we also have this fitting lengths. It should be a minimum 200, but not more than 1000, and it should be around 2% of each straight duct portion. What we don't have here for the conveying pipes is this kind of fitting sleeves that you know from the process gas ducts, because then you have a kind of piece where turbulences are and where can occur and has an initial point. So we only have this straight conveying pipes that are a little bit longer, so the fitting length, and then has to be fitted on site, so cut off to the needed length and then side welded.
Okay, understand.
Bolting, that's more or less with the extra amount, it's more or less the same what you have for the process gas ducts. So the bolting should be always a little bit more, because sometimes bolts, nuts and washers are getting loosened on site during erection. So that's the reason why we have this extra amount. What you see before, I come back to one typical. Yes, we had that drawing before. especially when you have the supports. And here you have this channel section, and as you know, the inside of the channel section is a little bit inclined. And for these channel sections, or when you have I-beams, then special washers has to be used. Do you know that? So this little inclined washers. Have you ever seen that?
I never ever seen that.
Okay.
So, for example, we have the inclined structure. So we insert the.
No, it's not coming from the structure itself. It's coming from the shape of this channel section. Yeah, just give me a second.
Is this fabricate or channels?
Okay, let's have a look on this picture.
Yeah.
It's only example, but here you can see this channel section, and it's a little bit inclined here on this inside. And when you put a bolting here through, and you would use a normal washer, then this washer will also be inclined, and you cannot tighten the bolt connection very well. And for this purpose, there are special washers that you can use. Just give me a second.
Use spring washer, right?
No, it's not a spring washer.
Ah.
Here you can see.
Ah, okay.
I think this picture is good. Okay, it's Chinese, but
but the first time I see this type of washer.
Okay. So as you can see here, also the washer has this inclination, and that is can be specially used for this use channels as well as I sections. So not this HEB sections that don't have this inclination, but when you have a small I section which is not that wide, you also have this little inclination, and for that you also get this type of washers. Usually for the supports, they should be already right in the parts list, but maybe you have a special construction or whatever with those U channels or I beams, then these washers should be used. Okay. So here you can see it here. This washers, and here you can also see the standard, and with the standard you can find it in SAP or in this ML-BOM for parts list creation. Okay. Yeah, welding is nothing new for you. About the welding sizes, fillet weld is with 0.7 or 0.5 thickness, depending on the plate thickness. And if you have butt welds, then it should be fully depth with 1.0 of the plate thickness. That's nothing new. That's also what we are doing for the process gas ducts. Also, corrosion protection. It's more or less the same. No, it's not the same as for process gas ducts, because process gas ducts are mostly insulated. These conveying pipes are usually not insulated, and then we have this system 1 inside and system 2 outside. Okay, then here are some.
Can you talk about what is the system 1 and system 2, because I'm not clear about it. Can you talk about this?
Okay. It's a standardized corrosion protection system from Polysius, and this system 1 is usually only a transport protection, and it's a reddish brown paint coat, quite thin, and it's more or less only for transport purposes, or when the pipes are laying a longer time on site until they are installed, and it's only a basic paint protection or corrosion protection, and that's the reason why we only apply it inside. For the outside, usually we have this system 2, and that depends a little bit on the contract. So for each contract, this corrosion protection system is set from the contract management, and it depends. So sometimes it is only one layer of paint coat, or sometimes it could be up to 2 or 3 layers of paint coat in a specific color, in a specific type of paint that has to be used, and so this depends a little bit. And Polysis is usually so that you don't have to know exactly in each contract which paint coat has to be applied. Polysis use this paint coat systems, because then you can also use standard drawings, and we only write down in the standard drawings and its part list that we would like to use this system 2, let's say, on the outside, and then we attach a further data sheet which is contract related to this parts list, and then for the fabricator is clear, okay, I have to use system 2, and then he has to look into this specific contract data sheet, and then he has to know what paint coat he has to apply. That's the reason why we use this paint coat systems.
Yeah, thank you.
So in the end of the day, for you, it's quite easy in the parts list. These paint coat systems have always the same material number, and you only have to write down in the parts list for inside system 1 and for outside system 2 for this conveying pipes. Okay. Then for the plant design, there are some requirements. Some requirements are reflecting here to other chapters. What is written down there? Let's say for the supports, that they should be every 6 meter and 60 meter between fixed points. But there are also some further requirements for plant design. Here, that's what I talked before. It should be avoided that 2 bands are next to each other. Of course, you can do it very rarely in one conveying duct, so 1 or 2 times shouldn't be a big problem. But if you do it 3, 4, 5 times, then the process step should be involved. And but on other hand, usually you should have this 20 times of pipe diameter between 2 bands, so that the material and the gas flow inside the conveying pipe can accelerate again. And that's what is written here. Then usually after a feeder, pump or blower, there should be also first a straight portion of a conveying pipe. From process that we got this information that also the straight conveying pipe should be 20 times of the nominal diameter. That has more or less the same reason as it is here for the bands, so that the material after the blower or the pump can accelerate. That's something special. That's currently not for AFACON. Then here's some advise it. I know that it cannot be achieved every time, because it depends on the plant design. Conveying pipe shall be as short as possible with less bands as possible, because every band will have a pressure drop. Every band, especially for basalt bands, are quite expensive. So, but yeah, of course, it's a thing for plant design, and it cannot be avoided always. Then what I was talking right in the beginning of our training is that for the loads, we have standardized them So we are not calculating the loads for each conveying pipe, and this standardization is depending on the diameter and what kind of support you have. Is it at a horizontal conveying pipe? Is it as a vertical pipe conveying pipe? And then what type of support you have. Is it a loose point? Is it a fixed point? And for all these different combinations, we have this standardized loads. And these standardized loads are based on a 6 meter support distance. So if you have less support distance, I would also write down every time this loads. I would not defer from it, because then you have to calculate individually. So let's say you only have a distance of 5 meter. I would assume the values here from the table. So not going too much into detail. And here you can see the horizontal loads in lateral direction and also in axial direction, and you can see here the vertical loads depending on if you have no basalt bands or concrete bands, it's in this column, or if you have basalt or concrete bands, then you have to choose this column. Nevertheless, it's not a thing. These load tables are not a thing for conveying pipe detailing. It's more a thing for the plant design and which loads they have to write down on their general arrangement drawing for later for the structural engineers. But nevertheless, it's written down here in this planning documentation.
It means we should write down the total load directly on the GA drawing.
Yes.
To send to plant design.
Yeah, it's the thing of the plant design, so they have to be on the general arrangement drawing and not on the workshop drawing for this conveying pipe.
Yeah. Okay.
As you can see, it's quite a huge table. I will not go into detail of it, but you can see the loads for all the different diameters, and yeah. Yeah, that's later. That's a thing for design reviews. That's nothing that is interesting for the detail design. So I will not go into detail on this page. Yeah, that's more or less the secret behind conveying pipes. Regarding the workflow for conveying pipes, it's usually like that the plant design is designing the conveying pipes, so it's routing and all that stuff, and then my team and we will directly talk to plant design where to put fixed point and loose points. So plant design is deciding, okay, here can be a support, and we are then looking in detail what kind of support should be applied there, and where expansion pieces have to be applied and all that stuff. So this is a work that is before detail engineering of conveying pipes, and when all those things are clear, then you usually get the information from us about this conveying pipe, means the routing that we have to see later in detail how we do it. With the Indian colleagues, we usually use the general arrangement drawing, or we do a step extract from E3D, what has been used for the detail engineering. Yeah, we have to see how we do it with you in Hanoi. Maybe we also give you a step file, or you can also use the data directly from E3D, like you do it for the process gas ducts that we have to see later. And then you can directly start with the detailed drawings. So it's a little bit different as we have it for the process gas duct. So we have no kind of basic engineering as we have it for the process gas ducts, because you don't have to calculate the loads for in detail because they are already in the plant design, and we also don't have to, or you don't have to prepare a GA because you can directly start with the fabrication drawing. So that's a little bit easier. Yeah, and
Yes.
then that's usually the workflow. Then you afterwards you send detailed drawings to us. Parts list should be in SAP. We will have a check on it, and that's it.
Yeah.
So it's a little bit simpler as for process gas ducts.
Yeah. Okay.
Yeah. So then what I will send you later, as you can see here, I already built up quite a lot of folders for you that I will send you later. So here you can find this catalog for the basalt pipes. Then I put in quite a lot of example drawings in here, where you can go through, but in the end of the day, it's more or less always the same. Of course, the routing is different, but the principle is always the same. Maybe we can have a look in one of it. Okay, that's good. That's a quite simple conveying pipe. Usually on the first page we have the overall routing in some views if necessary, some further sections if they are needed, and it depends on the size of the conveying pipes. Here in this case, the Indian colleagues already show the different kinds of supports that are used for this conveying pipes, and also some drawing text. And when you go on the second page, then you have this conveying pipe in detail with all the lengths, and here you can see there's a built-in fitting length with the side weld, and also then the details about flanges, how the flanges have to be applied, how electrical bridgings and all that stuff have to be applied, how in this case we have this silo inlet, how it has to be applied. So these drawings are quite standardized. So most of the details are always that are coming from the Indian colleagues are always looking the same. So as you can see here, there are no dimensions on it. They always use the same typical for each drawing. So it's quite standardized. And of course you can directly use it, copy it, or if you would like, and that's also on your choice. If they mainly do it completely in AutoCAD, so but in the end of the day it's on your choice if you also would like to do it in AutoCAD, or if you would like to switch over to Inventor. That depends on you, how it's more convenient for you. Yes. So most of these conveying pipes are looking more or less the same. It's always the same principle.
Now I have a question.
Yes.
Why don't we use isometric for solder? The fabrication for conveying pipe? Because I think if we use isometric, maybe we don't need to create the detail drawing. We only import from the E3D, and we have the ISO and fabrication inside.
Yeah, the thing is why we don't use this isometric types is that so the standards in those conveying pipes are more or less an internal thing. So for this isometrics, as you maybe know it from utility pipes, then quite a lot of things are detailed or cut off and so on site directly. So there you have a listing about real standard parts like flanges and all those supports and all that stuff you can buy from the market, and that's the reason why it is okay to have this isometric drawings with parts list about real standard parts that you can purchase direct from the market. But here for those ones that are more internal standards, like the supports and also the flanges, are not always something that you can buy from the market, especially when you connect to these basalt pipes. And that's the reason why we are doing more or less real fabrication drawings and not these isometric drawings.
Yeah, thank you for your answer.
Okay. So I will send you all of those example drawings that you can study in detail, or when later we will start with the detailing for ERFACON, where you can find quite a lot of examples and all that things. Then, of course, I will again send you this planning documentation. So this one, that's also in there. And then all those standard drawings we are using for the conveying pipes, bridgings, expansion tubes, supports, and all that things. That you have it on your side. Yeah.
Okay, Peter, I think after the view the fabrication drawing for by conveying, we will study or not. After that, if we have any question on the detailed drawing, we will go to you.
Yeah, of course.
Yeah.
I think most of the questions will come when you are working directly on it.
Yes, I think.
Then we will maybe do a training on the job, or then you say, okay, now we start with it, and let's have a Teams meeting 1 hour because we have some special questions, and that we can do then. So the today training shall give you only, let's say, a quick overview about the conveying pipes, how we deal with it, and the details will come after when you start directly working with that.
Yes, I think so. It's better when we work directly in the contract. There's some problem and question and things that us to add in.
Yeah. That's no problem. So don't hesitate in this case to contact me then, and then we can talk about all that thing. As you can see, it's also it's no rocket science. So that's not that complicated. I think the work you are doing very, very well for the process gas ducts is more complicated than this conveying pipes here.
Yes. Okay. For the contract, I have ERFACON. I think for the effective for this training, could you spend a little time to review with us on directly on the project? That mean we will show you the model for pipe conveying on each project.
Yeah, we can do it in another appointment. I think then it's also good to have Uli on this too. So maybe I have to talk to him how far the planning is and how much sense it makes. But we should do it in with 3 parties together, because I can say quite a lot of the details, but Ulrich is responsible for the plant design, and then we have to maybe have a review on what you have done in E3D.
Okay. Yeah.
Or what do you think, Uli?
Yes, I think we have to first find our routing and fixing, and then we can talk about. I think this is a row in which we work. We should work.
Yeah, maybe I don't know when we can do such an appointment.
I would say we have a deadline up to the 18th of October. So there we have to fix and or freeze our model for the client as IFI status or state.
Okay.
And so I think somewhere between, maybe 1 week before, that we can clarify the open points. So
Yeah, maybe then we should have an appointment in the week of the 7th October, something like there. Then you have more or less 1.5 week or 2 weeks until finishing. Maybe
I would say for also in this time up to the 18th of October we should find some of the basics for this routing. Then after this, then we will get into the detailed phase. So I think there is only important where we bring our fixations in position, and then after this, if the client agrees, so then we can detail our routing and construction. Then.
Yeah. Okay, maybe then in before the 18th of October, that's more a thing between you and Vietnam, and maybe I can also come to this if there are some general things where I can help, and afterwards we will go into the detail.
Yes, I would say this is correct.
Yeah, but nevertheless, you are always in contact with Hanoi, and when there is something I can come to you and help you, then give me a call.
If in every case if we have questions, then we will call up.
Yeah, of course. Okay.
Yeah.
Are there any further questions from your side?
At the moment, no.
Okay.
Yeah, I already asked all question.
Okay.
Now
then
I will
comes with the work.
Yeah, of course. Okay, then I will collect all the standards and drawings and all that stuff and send it over to you, and then you can have a further look on it. Yeah.
Okay, thank you.
Okay.
Thank you for valuable training.
Thank you very much for your time, and
Thank you very much.
have a great afternoon.
Yes. Okay, thank you very much, and have a nice day.
Have a nice
Thank
day.
you. Bye-bye.
Bye-bye.
Bye. Thank you. Bye.